All right, so welcome everybody. As we mentioned probably in the emails that you've received, we are doing this program on the mathematical laws of morphology and biomechanics. There are several seminars upcoming. One was a couple of weeks, 2-3 weeks ago by Professor Goreri, and there are many others upcoming. Part of the program involves these working groups, which involves some sort of a lecture. One of them is the one that Kathleen is going to give today, but also some interaction between the participants with the idea of building some sort of community, but also try to think about possible interesting things that mathematical and computational methods can do for problems in biomechanics and morphology. And of course, everybody's very welcome to propose things of interest. And maybe at the end of the first meeting, we will, maybe introduce each other's and talk about our interests. So we will follow mainly some of the topics covered in one specific book, which you can see in the working groups series about animal locomotion. So it's the reference is mentioned there, and Kathleen is going to mention her towards the end of her lecture. I don't know how much we are going to be able to cover, but tentatively, so the book covers many things. We were thinking about, specifically terrestrial locomotion, but we start with some sort of introduction with chapter 1 and chapter 2. Okay, so I think we can start with the seminar. So I'm very happy to introduce Kathleen Foster from Ball State University. She's in the Department of Biology. We are collaborators, and she works mainly in biomechanics and working together on several projects. In particular, all of these research direction is related to the laws of morphology and biomechanics in some particular species of geckos. Okay. But of course, today we're going to talk about introduction to the working groups and to the topics of terrestrial locomotion. So I think I've talked enough, and now it's time for Kathleen to start the presentation.
Thanks, Alessandro. Yeah, so let's get going. I was just showing you around the website as Alessandro was speaking. Many of you guys are already familiar with the website, so in fact that's how you found us in many cases. So I won't flip around anymore. I will just get the presentation going. Hopefully everyone can see my slides okay. Hopefully it says it's sharing, so there you go. Okay. So welcome to the working groups. I'm very happy to start this going. This is sort of a passionate topic of mine and Alessandro's, and we're hoping to sort of spur a lot of really nice conversations moving forward. So I think I just want to sort of start with the beginning of life. I mean, the theme of this talk is going to have a lot to do with diversity, and that diversity starts really a long time ago. The solar system was born around 4.5 billion years ago. Organic life, we have evidence in the fossil record of organic life around 3.7 billion years ago. Multicellular macroscopic life sort of took off around 0.8 billion years ago. And then we have some famous, very well recorded explosions of diversity. For example, like the Cambrian explosion that was about 500 million years ago. And that's when we really start to see animals in particular exploding in terms of their morphology and the environments that they invade. And we have many extant examples of diversity, an extraordinary variety of various forms and shapes of animals, and these are just a few that I've pulled up from the internet. Invertebrates and vertebrates, even if I'm a little more allied towards the vertebrate side. Invertebrate diversity is extraordinary. And all sorts of questions sort of pop into your head as you're looking at these kinds of things, or at least into my head. This kind of diversity is really inspiring. And of course, all of these animals live in all sorts of different environments. We have a variety of ones showing here. We have the arboreal environment, mangroves, rivers, coral reefs, deserts, intertidal, hydrothermal vents, the top peaks of Mount Everest, for example. We have life in all of these different places. And you could argue that the diversity that we see in the animal kingdom is in response to the diversity of habitats that they're able to live in. It's how species change through time to suit the environments, to be able to move into new environments and take advantage of unexploited niches. So it's natural that there's a corresponding diversity in a way between the environments that the animals live in and the animals themselves. And so we can go back in time and ask questions retrospectively about how animals have evolved in the past to survive these environments. What forms, what evolutionary pressures have led to the forms that we see now? And presumably that's in response, in many cases, to selective pressures that have happened and occurred in the past. And so evolutionary biologists try to piece together these various fragments of information, from molecular information, developmental information, morphological information that we can get from the fossil record. And it's probably important to note at this point that I'm not trying to argue that every change that we see is the result of natural selection and adaptive processes. A lot of the time, what we're looking at is the evidence of random processes, things that happen by chance, random dramatic events, disasters, isolation events that lead to changes in the genotypes and the phenotypes of the populations as they move forward. So although it's tempting to attribute adaptive significance to every morphological difference that we see in the animal kingdom, of course we can't do that. There's a fantastic paper talking about the spandrels of St. Marcos that probably every first-year biology student is familiar with, sort of arguing some of these cases. But this last quote here that I have on the slide here by Malcolm S. Gordon, who's the first author of the textbook that we're sort of basing this on, he talks about how biologists might be viewed as practitioners of evolutionary forensics, sort of trying to piece together these various clues from whatever happens to be preserved in the fossil record. And that isn't a complete record by any instance, but by any measure, by any standard. So it's kind of interesting seeing the stories that you can piece together, and certainly all the various tantalizing theories. One of my favorites is this sort of water to land transition that we see in the evolution of tetrapods, which I'm showing you in the figure here at the bottom, where we look at some of the ancestral tetrapods as they evolve through time, and these various representatives that we see in the fossil record as we go from a fish-like ancestor to a tetrapod, and where the various elements of the forelimb bones come from. And so it's fun to piece together these stories and to speculate about these things. And certainly we have some pretty good fossil records to help us with that. And that's the retrospective sort of point of view or strategy. And of course, we are interested in going beyond that. Many researchers are focused on, okay, so what's going to happen in the future? How are animals going to respond to things that are happening now? Conservation efforts are heavily founded in this. There's all sorts of changes. The Earth is constantly changing in its climate. Certainly, there's arguments for anthropogenic influences in terms of how it's accelerating things, all the various other things that we're doing, not just to climate, but to the structural environment. For example, building structures. A lot of species handle disturbed habitats very well and a lot don't. And so how is that going to impact the morphology and the survival and the fitness of all these animals moving forward? And of course, other random weather events or geological events, like volcano eruptions or huge storms, hurricanes, as we're coming out of hurricane season now. All of these things can have a big impact on animals, and represent major selective pressures that they're experiencing, and they have to come up with, if you want to anthropomorphize, strategies to deal with them. And so I think when we're looking at these sort of retrospective or prospective kinds of questions, it's useful to think about, to take a step back and think about what structures and properties and functions are the animals able to change? What do they have to deal with? What's the raw material that we're dealing with? So animals are very hierarchical structures. I'm not showing you every organ or every level of organization here, of course, but we can go all the way back to atoms, subatomic, if you want to go that far. Atoms coming together into molecules, molecules coming together into things like genes, the genetic makeup of the organisms that are determining our phenotypes, the cells that come together to make up various tissues, and the tissues that come together to make up organs, and then organ systems. And then you can come together to the whole organism. And you might be tempted to stop there, and many do. But then, of course, you can go even further and look at how organisms are interacting within populations of the same species, or how different species come together to form these various communities, and the various communities coming together to form ecosystems. So we can look at any single one of these various levels of organization as you go up this hierarchy and see selective pressures acting on these different levels. Something that is interesting to me as a biomechanist and isn't sort of represented in any single one of these, although the video kind of argues for it, is behavior. Behavior isn't a single, physical thing like all the other things that I was just talking about. It's an emergent property. Emergent properties are properties of a larger system that can't necessarily be predicted purely based on the combination of the smaller sort of constituent components that are coming together. And behavior is a really good example of an emergent property, because animals are capable of performing all sorts of different behaviors with their same morphologies, with the same underlying cells, with the same organ systems. That single confined organism interacts with its physical environment and with other species around it in different ways at different times. And so behavior is an excellent example of an emergent property. And we see lots of fantastic examples here. We have a chameleon moving slow motion as it bridges gaps in between different branches in the arboreal habitat. We have kangaroos boxing and fighting each other for mates. We have the basilisk running on water. We have these amazing birds of paradise doing all sorts of rather dramatic behaviors in order to attract mates. And then we have this fantastic kangaroo rattlesnake interaction. That's a video captured by my old PhD supervisor, Tim Hyam, and his collaborators in the field, where you can see that sort of predator-prey interaction and the very complex behaviors that are going in there. And so behavior comes into play, especially locomotor behavior, into probably almost every, if not every, critical function in an animal's life. Animals have to be able to... Whoa. Things are freezing slightly. Let's give it a second. There we go. Hopefully it won't jump too many slides. I'll stay there for a second. Okay. So animals have to be able to successfully perform their behaviors in the face of both abiotic and biotic challenges. So the abiotic environment, in terms of physical and chemical properties of the environment that they're living in and moving around in, and the biotic environment in terms of the predators and the competitors and the prey that they're interacting with. They have to be able to reproduce in order for their species to survive. And that often requires that they go out and search and find mates, attract those mates, or compete with others of their own species for mates. Together, survival plus reproduction comes together to determine the fitness or the ability of the animal to contribute to future generations of its own species. And that is central to the evolutionary process. So locomotion is integral to all of these activities: escaping from predators, capturing prey, dealing with competitors, either to get more resources or get a territory that's desirable or to get access to mates, attracting mates, finding them in the first place. All of these behaviors often require locomotion of some form or another. So it has a very profound impact on an animal's fitness or an animal's ability to contribute to that next generation. And of course, there's this absolutely fantastic quote that I love pulling in all the time, and that's that locomotion is the behavior that most dictates the morphology and physiology of animals. Thanks very much to Dickinson et al. In 2000 for providing that wonderful quote. And the videos. I'll let this sort of catch up. Hopefully people can still hear me. All right, there we go. A little break from videos. We'll go back if we can. I will try to scroll back. There we go. There we go. Okay. Heavy videos. It's hard when you're doing a video talk. Okay. So comparative biomechanics, comparative morphology, functional morphology, all are looking to investigate, often to investigate locomotion in some degree or another. It's in many cases we're dealing with biomechanical properties when we're looking at how an animal is formed, what its shape is, and all of these comparative efforts are sort of trying to investigate and take advantage perhaps of the enormous diversity of behaviors and morphologies and physiologies that we see. Using comparative methods, we can compare, as the name suggests, how different animals have managed to survive through time and succeed in their different environments, succeed in terms of survival and reproduction. And to see if we can identify the patterns in the variation that we see and perhaps speculate about some of the causes or the functional consequences of the diversity that we're seeing on the tree of life. And that requires knowledge of the evolutionary relationships, which of course is quite a big challenge. We always have theories. It's very difficult to prove them, but we can certainly have some well-supported theories in terms of the interaction or the evolutionary relationships between the species, and we have to incorporate that into our analyses. And a variety of researchers have come up with many useful tools that the rest of us can use, like this very quite famous Felsenstein 1985 paper. So we'll probably, hopefully, be talking about that in the weeks going forward. Some of the interesting statistical methods that we can use to incorporate evolutionary relationships into our analyses. Okay, there we go. So there's lots of, through these comparative analyses, there are lots of examples that we can use to help us see some of the more dramatic examples of evolutionary or adaptive changes. And convergence is a really useful concept in this case. We can think about the convergent gain of a variety of features. Flight is a good example, where we have invertebrates and various vertebrate groups independently evolving the ability to fly with different structures, but all independently in their lineages. I'm only showing one invertebrate group. I apologize to the invertebrate fans out there for not showing a greater diversity of invertebrates here. But we have birds and pterosaurs and bats all independently evolving flight. In the arboreal habitat, which is where I like thinking about most of my research, prehensile tail is a good example, evolving in multiple different groups: marsupials, kinkajous, primates, rodents, lizards, all having representatives that have independently evolved a prehensile tail because, 5 legs are better than 4 to help with such a difficult habitat. But we can also have convergent losses. We can have the loss of terrestriality, for example, when we have the sort of secondary return to a marine environment in the plesiosaurs, for example, or in cetaceans, where they've evolved to specialize in the aquatic environment again after having been on land. And then we have the geckos, which are a really good example of both repeated gains and losses of the adhesive system, depending on the habitats that the various groups have been able to exploit. And one of my favorite examples, and certainly an example that I draw on a lot in my own research, is convergence in the anolis system. So anolis lizards, for those of you not familiar with them, they are a genus of lizards that have really diversified a lot in the Caribbean. And on each of the Greater Antilles Islands, we have repeated evolution of what we call ecomorphs. And these are species that have repeatedly evolved similar morphologies and behaviors based on the particular area of the arboreal habitat that they're specializing in. And so here are some of the ecomorphs here from this figure from Losos 2009, and we can see some of the species that have specialized in the topmost crowns of the trees getting very large with very large heads, and nice big adhesive toe pads. And we have other ones that specialize a little bit close to the ground, or might even be considered a slightly more generalist, like the trunk ground species that are smaller and have different leg ratios. And all of these animals have various morphologies independently evolving in the different islands in order to help them deal with the particular challenges of the microhabitat that they're specialized for. And my work sort of goes into more of the biomechanics in each of those groups. For example, these are some videos of 3 species from Puerto Rico belonging to 3 different ecomorphs: a trunk ground ecomorph, a trunk crown ecomorph, and a grass bush ecomorph. And these are all, running across perch diameters that are approximately similar size relative to their limbs. And I study their biomechanics and their muscle function in these species, just to get an idea of how they're dealing with the challenges of arboreal habitat and whether or not the different ecomorphs are handling those challenges similarly or differently. So that's sort of where my academic heart lies. So we have a lot of challenges that we face with biomechanical data. Certainly I face with biomechanical data. Oh, I did it again. There we go. Including scaling for size. This is certainly something that morphologists, that pretty much every organismal biologist has to deal with if they're going to be comparing anything, either within species as they develop or across species as we're dealing with different sizes. Body size changes, and with that body size change, a whole suite of other things can be changing. And there's all sorts of questions related to allometry, the relative proportions of the different bodies as they're growing or in the different species. And we have to make sure that, statistically speaking, we're not letting size sort of drown out any other questions of interest. Certainly that can be our question of interest, but if we're interested, for example, in running speed, and we're comparing animals across different sizes, how do we know we're not dealing with the change in size as opposed to changes in running speed? So we have to make sure that we can come up with a way to account for that. And there is a lot of discussion in the literature about the right way to do that, and it certainly has been done in many different ways in the past. We could ask questions such as, what measure of size should we use? Should we be using mass to account for body size, or length of the body, or length of the head, or length of a limb, or how are we going to quantify body size? And then how are we going to incorporate that scaling into the analyses? And residuals and ratios are common ways of doing that, and they have, their advantages and disadvantages. We also have challenges related to the high variability in the environment and in the animals. If you've noticed nothing so far in this presentation, we're talking about a whole lot of animal diversity here, and this is certainly a larger amount of variation than maybe you might experience in other branches of the physical sciences, like chemistry or physics might be dealing with less variation than what we see and what we're dealing with the animals. Not only are we dealing with a huge diversity of morphologies, but we're adding this sort of ephemeral, this like emergent property of behavior when the animal's doing whatever the heck it wants to be doing rather than what we want it to be doing in our experiments. So we're dealing with a lot of variation, and so statistics is an inevitability, and certainly a very large challenge trying to figure out how to deal with that variation, how to maybe use it to our best advantage, and sort of what statistical and mathematical approaches we need to take in order to answer our research questions of interest. And then we're dealing with multivariate systems. I already talked about how animals are hierarchical in their organization, and certainly even just the few levels of organization that I deal with are highly multivariate. Even if we're like how an animal is built, how its morphology is put together, and how that morphology comes together to function is the culmination of a lot of complex interactions between the various levels of organization. And so simple univariate or deterministic approaches are often not sufficient to get a good picture of the mechanisms underlying what the animals are doing, why they're shaped the way they are, what's determining their morphology and their biomechanics. Just using locomotor biomechanics as an example, when an animal is running, most of us are not necessarily interested in just how fast the animal's running, but things about how it's running. So we can measure joint angles and angular velocities as well. And we can, even just restricting it to that, there's joint angles and angular velocities for all the joints, for all the little intervertebral angles that we're dealing with if we're looking at the body undulations at the same time. So just considering those two sort of families of variables, we have a lot to deal with. And that's just biomechanics. We could add a whole other level of organization. For example, this is muscle trace electromyography recording from the gastrocnemius, the calf muscle of the animal that you're seeing up there, the Anolis equestris running. And so in addition to all the biomechanical variables, we could simultaneously be looking at things related to muscle function, activation and deactivation, recruitment of muscle fibers. We could also be looking at the neural activity, other physiological properties, cardiovascular function. We could be incorporating information from all of these different organ systems and at the same time. And that just adds whole other levels of organization that we have to deal with. So extremely multivariate. And how do we do that? There are some various ways that math and physics can help, and I'm certainly not the one to talk to about that. That's the point of these collaborations, as far as I'm concerned. And so we want to sort of draw on some of these tools. For example, fractals and the idea behind fractals have been used to understand the distribution and the number of blood vessels as you go from the very few large arteries and veins into the arterioles and the venules and down into the capillaries. We increase in number of those blood vessels as the diameter decreases and it distributes around the body. And so fractals have been used by others in order to understand that distribution of the blood through the circulatory system. Thermodynamics has been used to understand the fluxes of energy or nutrients or materials through biochemical processes or through ontogeny. We have geometric transformations like conformal transformations that were proposed by Darcy Thompson, for example, to understand variation in animal shapes. And so we can draw on these kinds of mathematical tools and physical tools to help us understand these complex systems at the organismal level, which Alessandro and I both think is a little bit lacking. I mean, it would be really nice to explore this more and to see the insights that we can gain into these kinds of complex systems. So moving forward in these working groups, many of our discussions are going to begin with or get inspiration from this book. This is what I sort of structured my talk off of, the first chapter. And this is Animal Locomotion, Physical Principles and Adaptations by Gordon et al. And so we're going to be sort of piecing together some lectures from the materials as we move forward. And our goal is to stimulate discussion, to find some common points of interest for collaborative efforts amongst those who are joining the working groups, and perhaps find ways to make progress in the fields of biomechanics or morphology or ontogeny through the use of these mathematical and statistical tools. So ideally, people will hopefully be coming with some issues or some side projects that they've sort of pushed aside because they didn't have the expertise they needed, or sort of hit a roadblock or deprioritized it for one reason or another, and would really like to make progress on that and join this sort of a collaborative, hopefully internationally collaborative working group, and we can sort of work towards some productive outcomes. So just to remind people of the websites, I just wanted to throw it up here. The website for the whole program and my and Alessandro's contact information for those who want to reach out to us directly. Of course, we have Slack channels. We have all sorts of ways to interact, and hopefully we can have some great interactions moving forward.